Okay, so today it's my pleasure to introduce David Hogg from New York University. David did his PhD at Caltech. In 1997, he moved to the Institute for Advanced Study at Princeton. In 2001, he came to New York University, and since 2007, is professor of physics and data science in the Center for Cosmology and Particle Physics in the New York University. New York University. His main research interests are in observational cosmology. He's strongly involved in the SDSS survey, and today he's going to talk about information theory for astronomy. David?
Good, thank you. And you can see my slides. Oh, I have to say got it, then I'm being good. Okay, good. Good, so I'm going to talk about information theory, and this talk is a little bit pedagogical, so I apologize. I don't mean to come to Cambridge and tell Cambridge how to do their science, but actually I kind of do. Well, I don't really, but I do think there's some ideas in its information theory. And if you're a cosmologist and your background is cosmology, you probably know a lot of this, especially in the early slides. So you'll just have to nod, and then we'll see. Hopefully there'll be something useful here as we go. It's going to be a little pedagogical though. I do think it's useful to think in terms of information theory. It's helped me a lot in my own research. And I should say, as I was saying to the grad students earlier, my research is about making precise measurements or hard measurements. I like making hard measurements, like you've got an instrument that's hard to calibrate and you're trying to find a signal that's tiny. I love that kind of problem. That's why I like extreme precision radial velocity, like Terra hunting experiment, because it's a hard hardware problem and it's a very tiny signal and it matters to us. And I found information theory to be very useful in thinking about problems like that. Okay, good. So let's get into it. What is information? So imagine you're measuring the brightness of a star and you have a photometer on that star. As time goes on, you collect counts from the star. And as you get more and more counts, you get more and more precise measurement of the star. And your variance goes down with time. Your inverse variance goes up linearly with time. And that inverse variance is called the information. The information you have about the brightness of the star is the inverse variance of your estimate of the brightness of the star. And for me, usually information is an inverse variance. We're also going to talk about entropy in just a few seconds. But it really is that simple. We're talking about inverse variance. And you might think, how much can you give a whole talk about inverse variance? Well, it turns out I can. But of course, I've also written 100 pages on the archive about fitting a straight line. So that's where we're at. There are people's names associated with information theory. And like all things in physics, the names that are associated with it are the wrong names. However, there's a bound called the Kramer-Rao bound. And you'll see it in some abstracts of papers that I've written, and you'll see it on some figures later. I usually call the information theory thing the Kramer-Rao bound, but first of all, I'm mispronouncing the name Kramer. And second of all, there were a lot of other people who did that work. And the bound is like a fundamental limit in frequentism on how well you can make a measurement. And it also applies to Bayes too in some modified form, but it's really, it predates Bayes, well, it doesn't predate Bayes, but it predates our kind of Bayesian thinking. Fisher information is something that the cosmologists care about a lot. And really, I'm mainly going to talk about Fisher information actually here. Again, named after maybe the wrong person, but whatever. And then I have to mention David Mackay, who you all know, and who was well, it's tragic for so many reasons that he's dead, but his book, this book that I cite here, first of all, it's free online because Mackay was such a believer in that. And second of all, it is where I learned all of this. And I cannot recommend it highly enough. I mean, it's literally so pleasurable. You can just read it. It's like the opposite of Jackson E&M. It's the opposite of the textbooks we're used to. It's just a pleasure to read this book. Although I love Jackson, I have to say, but whatever. And then I'm not really going to talk about Shannon, but there's also this idea of like Shannon information, the information that about traveling on a wire, and I'm not really going to talk about it, but it's also a very interesting set of subjects, also probably named after the wrong person, but whatever. Actually, I shouldn't say that. in all these cases, Shannon is a good example. Shannon's book in 1948 is also amazing. If you haven't read it, it's such a pleasure to read that book. It's so simple, very short. It was like a technical report or something from Bell Labs. It's now published as a little paper, a little book or a paper. And I think it's 1948, and it's just so beautiful. It just, every step of the way is really easy to understand. And then at the end of it, it shows that entropy is related to communication over a channel. It's amazing. So and I'm not going to talk, I have a slide here, but I'm not going to talk about this at all. I'm just putting it up here for context if you're kind of more theoretical. There's a formulation of statistical physics, which actually maybe started in Cambridge, but I don't know, which is that the coarse graining or that exists, to have an entropy, you have to have a coarse graining because you have to have like some set of states that you can sum over to talk about the entropy. And you can see this as being about the knowledge of the experimenter or the investigator. And that's a very Bayesian concept. And that's sort of the way that knowledge, so Bayesian inference is about knowledge. And once statistical mechanics becomes about knowledge, then you can see that the concept of entropy will be common to both. But I'm really not going to talk about entropy hereafter. I'm really going to use that Fisher formulation of information going through. But everything I say could also be translated into the entropy language if you wanted. Oh, and I just say here, I just summarize stuff about Shannon. I will give you, my slides are public. I'll put a link up to my slides. Can I get rid of the icon? Is there an icon? Jane's book is as interesting as Mackay's, George says. I agree with that. I love James's book. I really enjoy it, but James's book is kind of like irritating. There's times when I want to like tear it in half, whereas Mackay's book is just, I think it's flawless. I don't have a single complaint.
James was given a tough time by the traditional statisticians, and
that's true. He was battle hardened, whereas Mackay had a much comfier environment. That's true. Right. That is true. Mackay also, I have to say, many of my colleagues that I work with in computer science and statistics and applied math spent time in Mackay's group. Mackay generated so many good people. The impact on human knowledge is immense. One important idea, I think, is that only differences of information are relevant in the same way that differences of energy and differences of entropy are relevant in physics. Differences of information are really what happens. If you're Bayesian, it's the difference between the posterior and the prior. If your posterior is not much better than your prior, then you haven't learned very much. And if you're a frequentist, it's about the variance in your estimator. If after your experiment, your estimator doesn't have a lower variance, you haven't learned very much. And so it's the difference in the inverse variance that's going to be the information that we're looking for. I said cosmologists have thought about things in terms of information theory for a while. Actually, when I was a postdoc, there were all these cosmology postdocs at the Institute for Advanced Study, and we discovered the baryon acoustic feature. But Eisenstein and Hu and Tegmark and so on, all these cosmologists around, and they brought a lot of ideas from Bayesian inference into cosmology, thinking about likelihood functions, and naturally that led to thinking about Fisher information and predicting the outcomes of experiments. And I don't know if it was really them. There were lots of other people around doing that, but cosmology is a natural place to do it. And there's this, and you see it in these kind of forecasting papers. And there was this important thing from the early 2000s called the Dark Energy Task Force, which made some statements about like what kinds of projects should we do next in cosmology, and how do we think about which projects to spend more money on, and what's the value of a project. And they actually ended up giving an information theoretic metric for projects in cosmology. And here's a figure from the Dark Energy Task Force final report, which says that the Dark Energy Task Force figure of merit is the reciprocal of the area of the error ellipse in this plane of two cosmological parameters that are of no interest to me. Actually, I guess they are of interest to me, but I'm kind of out of the precision cosmology world, so I don't pay attention to the accelerating universe very much anymore. But they're more or less the accelerate. It's a parameter related to the acceleration, a physical model of the acceleration, and then some scale, some time dependence of that. And but they were making a very specific, when they say the reciprocal of the error of the error, the reciprocal of the area of the error ellipse, they're talking about an inverse variance. The error ellipse is representing a variance, and the reciprocal of that is the inverse of a variance. And so it's actually not quite the right units, but whatever, it's close. It is close to the units of information. And one comment to make about that context, the scientific context of like, why is Fisher information coming up in cosmology? One piece of context that's worth remembering is that cosmology, even in 2006, was an extremely mature field. There was a very well-defined cosmological model with 6 or 11 parameters or whatever it was. There's some number of parameters. They wanted to measure certain ones of them more than others. And so there was a very clear quantitative question in a very clear quantitative physical model that generated very clearly the kinds of data that would be measured. That is not the case for a lot of areas in astrophysics. So you can't apply this thinking to everything. And I'll come back to that when you can apply it and not in a minute. Information theory is more useful to you the closer you are to the state. And I use this word generative model there, and there's lots of Bayesians probably in my audience, but it's more or less, a generative model is more or less what you need if you're going to be a Bayesian. And of course, you don't have to be a Bayesian. In fact, my talk, I think I said a few slides ago that my talk would be frequentist safe. So I say here, note frequentism, this talk will be frequentist safe. You don't have to be Bayesian or frequent, it doesn't matter. Everything here applies. When I think about this stuff, I'm not particularly Bayesian, but I do think that the place where Bayes and frequentism intersect is at this concept of the likelihood function. And so for me, a generative model is a likelihood function, and then maybe priors over the parameters, or maybe priors over the parameters, the nuisance parameters, but it's like a probability for the data given parameters. You have to be able to say what data would be generated by this parameter. If you change this parameter, how would your data change? That's basically what you need to be able to, those are the kinds of questions you need to be able to answer. And that's what's generative about it. Your parameters generate your data. And so you are expecting a likelihood function, which is like a probability of data, which would be y here, a blob of data, like it would be positions of your galaxies in a cosmological simulation, given parameters, which would be like your 11 cosmological parameters would be A, and then B would be your nuisance parameters, which would be things like the calibration of your instrument or things you don't know about your window function or something like that. Good. So when I talk about a generative model or expectations for the data, I'm talking about this kind of framework. And so let me give you a reminder of things you already know, which is least square fitting. And I mentioned earlier, I've written more than 100 pages on least square fitting. In fact, even on fitting a straight line, there's 2 papers there that are together more than 100. And I'm sorry, I have like a slide page number, which interferes with my things there, but anyway, whatever. The idea is your data, which are y in this case, so you have many data points y sub I, and each data point can be written as a sum of functions of some features x. So you have some features x, and you have some data y, and you're trying to fit a linear model of the features to predict the data. So if it was like a CMB map, the features would be like positions on the sky. Say you're like modeling a foreground in the CMB map. X would be your position on the sky. Y would be the value of the map. And the GJs would be like the spherical harmonics that you're expanding into. So you expand out into spherical harmonics, and then you fit a linear combination of spherical harmonics to fit your map. So that's what one is representing. And then the idea is your data are generated by this linear sum plus some noise. Epsilon I is a little bit of noise, and that noise is drawn from something simple like a Gaussian. We're going to be very Gaussian for a bit. We'll come back to that a little bit later. Now, if you pack everything into big matrices, so you pack the featurized or the functions of your features, the GJs of the XIs, all those features into a big matrix X, which is a very big matrix. It's like number of I don't want to get this wrong. It's like number of functions you're using times number of data points. That's what X is like. And then A is the number of parameters you have. It's like a column vector of the number of parameters you have. And then the covariance matrix contains all your noise information. Oh, then you can write the linear model in the form called 6 here, which is that you can just write it as a single matrix multiply. And then when you sorry that I don't know how to get that to disappear. It's supposed to not be there. Ah, good. It let me alone. Was this working? Yes, good. So you can write it as single matrix multiply. And then there's a formula which I've written on the board. I love this formula so much. 8. That's my favorite equation in all of data analysis. And it comes up everywhere in data analysis, maybe in slightly different forms. That is the solution of linear least square fitting. With what's called weighted least squares by the statisticians. It's called chi-squared fitting by the astronomers. It's the C inverses are in there. So if you look at it from the right side over, there's a C inverse Y at the very right side. That's an inverse variance weighting of your data. And then you take your inverse variance weighted data and you project it onto the X's. That's like projecting it onto the basis functions. And then the thing in front is an inverse thing, which projects the basis functions onto each other. So you inverse weight the data and project onto the basis functions. You inverse variance weight the basis functions and project them onto each other. And then the ratio of those two things is your answer. It's so beautiful. And actually it has this nice like geometric interpretation. In fact, there are textbooks about statistics written purely in geometric language. It's like, this is an equation, 8 is an equation in geometry. It's like about a distance. It's finding the vector that finds the minimum distance to the data, it finds the different minimum distance between the data and the closest point in the models like linear subspace, where closest is defined by this inverse variance metric. So the inverse variance makes a metric and then you ask close, anyway, whatever. I can go on about it for ages. But 9, the C inverse is the uncertainty. It's the inverse variance on your parameters. So 8 is your parameters, your best estimate of the parameters, and then 9 is the inverse variance of the estimate of your parameters. And it's so beautiful. And 9 is the Fisher information. That is the Fisher information in this problem. It is just your estimate of the uncertainties on your answer. It's a covariance matrix that has uncertainties down the diagonal. It has inverse uncertainties down the diagonal and off diagonal things. And if you invert that thing, it's your errors. And then 11 is just rewriting that in terms of, instead of writing in terms of X, writing it in terms of the derivative of your model with respect to your parameters, which is the same thing. 9 and 11 are identical because the model is linear. That's the Fisher information. And so now you can, when you're doing undergrad physics lab, you do this, you fit a line and you get that answer and you put that error bar on the slope and intercept of your line or whatever. And then often you'll ask the students, is your error estimate reasonable? So when is it reasonable? It's reasonable when the noise in the data is close to Gaussian, for one. The uncertainty estimates you have are close to correct because you put them in, you did this inverse variance weighting. If you inverse variance weight with the wrong inverse variances, you'll get the wrong answer. And that the linear model is an accurate representation of the world. If the model doesn't, if the world is nowhere near this model, it doesn't really matter what you've computed here, it'll just be wrong. So these assumptions are very hard assumptions, and they're very hard, they're hard both in the sense that like those have to be true, and they're also hard in the sense that they're actually quite hard to verify in some cases. It's very hard to verify that your noise is Gaussian. It's very hard to verify your uncertainty estimates. In fact, usually our uncertainty estimates in most projects are made theoretically. They're not, often they aren't verified. They're based on like counts we got. And the whole point of science is to figure out whether this linear model is an accurate representation of the world. So these are hard, yeah. So the right way, I don't know what my next thing is. Right, so the right way to think about this information is not that it is your error estimate. That's not the right way to think about it. The right way to think about it is that it is the best you can possibly do. It is also the Kramer-Rao bound in this case. So the Fisher information is also the Kramer-Rao bound. It's the best, and the Kramer-Rao bound is a bound because it's the best you can do. And so under those assumptions, you'll get the right answer. This will be it. If your assumptions are wrong, and the world's worse, you will generally do worse. I can come up with adversarial counterexamples, but basically you'll do worse. So this is the best you can do. And so when you're doing an experiment, like say you're running terra hunting experiment and you want to find planets, you're going to compare your answers to this Fisher information. And if you're not close to it, you've got work to do. I'm in the terra hunting experiment, so I'm criticizing myself there. Good, and I don't know why I wrote it again. Oh, I know why I wrote it again. Just to say, I said something about a likelihood function. Where does that come in? So 14 rewrites 12. So 12 is what we had. 14 is the rewriting of 12 in terms of the likelihood function. -2 times the log of the likelihood function is chi-squared, more or less. Depends on whether your variances are parameters, but whatever. It's basically chi-squared is -2 log likelihood, and this is the second derivative of chi-squared at the minimum, or anywhere if it's linear, but at the minimum, or actually there's an e there in 14, there's an expectation value. So technically, the information has an expectation value in it. I don't want to talk about that. I know what that is, and I can talk about it, but it's just off topic for us for now. But feel free to ask. Okay, good. So a good example for information theory, since it's such an important problem in the world, right? Well, it's not an important problem in the world right now, but it's an important problem to astronomers, and it's an important problem in Cambridge, is how precisely can you measure the radial velocity of a star? We're going to spend a lot of money measuring radial velocities of stars over the next decade, not just at Cambridge, but everywhere. And how well are we doing? And what do we need to do well? Measuring a radial velocity of a star is a perfect, hey, Didier is in the house. I agree, Didier. How precisely can you measure radial velocity? So first of all, perfect application of these ideas, because there's a model being compared to data, and it's data that's taken at very high signals noise where the number counts are high. And so we actually think some things might be Gaussian about our data. And we have a very detailed stellar spectrum, which moves left and right in log wavelength coordinates as the velocity changes. So there's a very well-defined relationship of the model. We have a generative model. We think that if it's moving faster, it's shifted one way, and if it's moving slower, it's shifted the other way. It's really exactly the right problem to be thinking about. And so the information theory, the Fisher information, is that the inverse variance of the radial velocity should just be the inverse variance of the data sandwiched in between two derivative operators, which are the derivative of the spectrum with respect to radial velocity. And notice that those are big vectors, because like when we do a HARPS 3 extraction, it'll have, I don't know, actually Sam maybe knows, it'll have, I don't know, 150,000 pixels or something. So we'll have 150,000 pixel spectrum, and we'll have the error estimate at every one of those pixels. That will make C inverse, 150,000 by 150,000 matrix, huge matrix of error values. Hopefully it's very close to diagonal, because otherwise it's going to hurt. Gaia, for instance, is not close to diagonal, at least not in year 1. I think by year 10, it'll be in very diagonal, but it's not diagonal at the beginning. Hopefully our covariance matrix will be close to diagonal. And then we just basically do an inner product using that as the metric of the derivative of the spectrum with respect to velocity, with the spectrum with respect to velocity goes whoop down to a single scalar number. And that scalar number will be the inverse variance of the radial velocity measurement. Boom. Now, Didier is like really expecting that when I hit next on this slide, I'm going to say a number, but I'm not. I'm just going to say there are scalings. Here's roughly the scalings. The scalings are, so the information about the radial velocity increases if you increase the signal to noise. Duh. If you have smaller errors, you have larger inverse variance, you have more information. It also increases as the number of lines in the spectrum increases, which means as if you have more spectral range, so you see more spectral features, you're getting more information about the radial velocity. One way to think about it is each chunk of the spectrum is going to give you radial velocity information. And as you get more and more chunks, the information grows linearly as you add chunks. The depths of the lines will matter. If you have deeper lines, it's a stronger effect when you move the spectrum. So that means higher metallicities and lower temperatures are going to give you better radial velocity measurements. Also, your information will improve as your lines get narrower. If your lines are big and broad, they don't have nearly as big effect as if they're narrow. And that means you want to be at high resolution. And sure enough, HARPS 3 and Terra hunting experiment is designed to be a high resolution, high signal to noise measurements of high metallicity stars that will do these things well. And then, of course, there's this point about intrinsic noise in the star, which I'm going to come back to a little bit in a minute. Now, of course, one of the problems is that if you want to implement equation 15, you have to know the spectrum of the star. And of course, we don't know the spectrum of the star ab initio. Well, maybe some people think they do, but they don't, because stellar models are not good enough for these purposes at all. You have to be data-driven in this world. So what if you don't know the stellar spectrum accurately? That's something I work on here in New York with Megan Bedell. She's written a nice piece of software called Wobbly, which we're now extending in lots of different directions. And Wobbly takes a set of images, or takes a set of stellar spectra at very high resolution of the same star at different radial velocities, and it decomposes that set of spectra into a mean stellar spectrum and a set of radial velocities. And I'm not going to talk about it in detail right now. It's kind of an aside here, but I will say one thing, which is that it turns out you saturate the Kramer-Rao bound on radial velocity. You get to the Fisher information even if you don't know the spectrum in advance. Once you have something like 12, we don't have an exact number, but it's about 12. Once you have about 12 observations of the same star, the empirical spectrum that you get from averaging the stars is as good as any theoretical spectrum you might use, and almost certainly better. And so the Wobbly project is kind of motivated by the idea that we shouldn't be using theoretical templates. We should just be using data-driven templates, because once you have a few epochs, and projects like Terra hunting are looking at getting like 1,000 epochs, not 12. So, we're easily in this regime. By the way, I'm very proud of this figure, because these were, on the left is independently analyzed measurements of 51 Peg, and on the right is independently analyzed measurements of Barnard's star. And in both cases, Wobbly was just told, find the mean stellar spectrum and find the mean telluric spectrum, and check out the telluric spectrums. Those are those blue lines. It finds the same telluric model in the two cases, even though it was not told in advance which lines are telluric and which lines are due to the star. And look at that Barnard star spectrum. It's not like it's easy. But it turns out once you have a lot of epochs on a star and it's changing its radial velocity, you can clearly causally separate the telluric spectrum from the stellar spectrum. And that falls into a category of statistics called causal inference. This is like a causal inference of the Barnard star data. And you can see that the Barnard star data, this is just data driven. We didn't give it any first guess here. It just figures out that certain lines in the spectrum are fixed with respect to the observatory rest frame, and others move with the star. And look at the spectrum of Barnard star. Like, oh my goodness. And but one of the things that's interesting about it is that Barnard star, because it's a very cool star, the spectrum contains a huge amount of radial velocity information. And if you just use a standard template, you don't extract it all, because the standard template doesn't match that star well. Anyway, that was totally an aside, just showing off, because that's part of my job. So now, what about structured noise? I've talked only about trivial noise models. Every data point has a Gaussian error, but what if there's non-trivial noise going on? And there are non-trivial noise sources in stars. For instance, there's P modes. The stars are oscillating on timescales that are relevant to the observing times. Our observing times are like 10 minutes, 15 minutes, and stars like the sun oscillate on 5-ish minute timescales. So there are oscillations at the same timescale as the observations we're making. And those oscillations might look like noise, but it's not exactly stochastic, because over long periods, like there's, I don't know, several days of coherence time to the sun's oscillations. And so if you take observations like right next to each other, they'll actually be continuously correlated by this P mode stuff. And then there's also like really other kinds of stochastic noise with different correlation structure. There's plages and sunspots, and there's granulation, and there's like super granules, or so they're called something like. Anyway, there's all these different things happening on the surface of the star that create noise sources at different timescales. And I've represented those by ... because I mean, there's so many things you can add, but basically the noises add in the covariance matrix. And then the thing that appears in information theory is the inverse covariance matrix. So as you add these sources, in general, they hurt you from an information theory point of view. As you add more noise sources, you do less well. It reduces your information because it's lowering the inverse variance. And that makes sense. But, and I have a bold-faced thing here, if your noise is highly structured, there will be particular observing strategies favored. And I won't go into detail here, but there's a very nice paper by Chaplin recently that says that if you have P modes affecting your star, there's particular observing exposure times you should use. They're indicated by these red lines. And if you look at that thick gray line, that's like, what's the variance? So I'm plotting the variance, the inverse of information that you get out of an observation of a certain length of time. And if you choose those particular times, you get lower variances. And it's because you've chosen a time which is an integer number of oscillations. If you know the star is nearly coherently oscillating, you might want to integrate out those oscillations and kill them. And so that's a beautiful idea. That's in that Chaplin paper. It's really nice. What Megan Bedell and I are working on in New York right now is that there's even better strategies. There are strategies where instead of taking one exposure of the right length, you take 4 exposures of a different length, and you do even better at suppressing the noise because you learn the continuous motion of the surface of the star, and you can actually model it and fit it out. So you can like fit out the motion of the surface of the star as a nuisance parameter. And I'm going to talk more about nuisance parameters later, but the point I'm making here is that information theory is it's not just the fact that your noise, like that as you get more noise, you do worse. It's that you want to take observations that null your noise or avoid your noise. And when your noise has correlation structure, so I was just in a PhD defense by Lily Zhao, who's an excellent PhD just coming out of Yale, who works on EPRB. And she said in her talk, like the most optimistic assumption is that the noise is white. And I was like, yes, I agree with that. But if you have noise that's correlated, it isn't white noise anymore, it's correlated, and you know the correlation structure, you can exploit it. And you can do better. So this is an important point. Now, what about noise you don't understand? That's like talking about the noise you do understand. P modes are easy. We understand how stars oscillate. Okay, some people on this call might disagree with that, but more or less, we understand how stars oscillate. There's lots of other things on the star surface we don't understand at all. And there's no generic answer to this question. There's no way to truly know your noise process. Even if you know that the noise is Gaussian, you still need to know what the whole correlation structure is. And that's like measuring second moments. It's like measuring the power spectrum in large scale structure. And it's hard to do. You need a lot of data to measure that power spectrum. And it's basically very hard to do if the noise is Gaussian. And then if the noise isn't Gaussian, you need to know all the higher moments, which is truly impossible. And I'm going to come back to that point later in the talk. But basically, there's no surefire way to understand your noise completely. You always have to make assumptions. And that is like, well, there's a lot of Bayesians in my audience right now. They are all like, yeah, duh, you have to make assumptions to do anything. Right, you do. And this just makes it very, very abundantly clear. In order to measure anything about your noise model, you have to assume forms for it and then fit the parameters of those forms or infer them. If you really want to go Bayes, you can infer them simultaneously with the data analysis that you're doing. And I'm going to come back to that in just a few seconds. But John Bacall, who is my PhD and my postdoc advisor, liked to say that half of all 5 sigma results are wrong. Why? He didn't have an answer why. I think he was kind of cynical about astronomy, but I'm not really cynical about it. I think it's because there's aspects of your noise model you just can't understand. You can't empirically understand it. It's hard. So implications for RV observing strategies. This slide is for Sam and Didier and Annalise. We need to take RV data in such a way that we can exploit the noise structure. And that means we can't just observe every star every night. We have to make non-trivial observing footprints so we learn the correlation structure of the noise, and then we have to adapt our observing strategies to exploit the correlation structures we find. And we will find more planets. I guarantee it. I literally guarantee it. Good. I'm going to switch gears now. What about the Milky Way? Didier. Good. What about the Milky Way? So I'm also interested in the Milky Way, another thing that people work on here in Cambridge a lot. In fact, Cambridge is, it's a little scary to talk about the Milky Way in Cambridge with the Gaia experiment going on, which of course I love. And I hope everyone knows that Gaia has been my favorite activity in the last few years. And we've been running these projects, the Gaia sprints, that have really transformed my work in New York. And I've really enjoyed it. And it's just such a miracle to have 1 billion stars dropped on us for, we don't deserve it. It's amazing. And then we're doing I'm involved in SDSS-5 apogee, and I've been involved in SDSS-3 apogee and SDSS-4 apogee, and now I'm involved pretty heavily in SDSS-5 apogee. And one of the reasons that we're doing that project is to capitalize on the Gaia data. We are putting chemical abundances on stars in Gaia. And SDSS-5 apogee, there's some uncertainties about our hardware setup, and we got delayed by the pandemic, but the goal is to get abundances for of order 5 million stars with a focus on red giants so that we see a map of a large part of the Milky Way, not just the little neighborhood. And if we do these projects, and we are doing these projects, we better learn a lot about the Milky Way. It better not just be like, cool, it conforms to our expectations. We better learn lots of new things because these are expensive projects. And so that kind of ties into this ethical aspect. There's an ethical aspect of data analysis. I mean, I don't want to pump it up too much because I don't want to really measure I did decide to be an astronomer, which is debatable ethically, like from the beginning, but whatever. But if we are going to spend public money to do big projects, we better be saturating the information theory bounds if we can, because what are we doing? And so I've done a number of projects on the Milky Way related to how do we measure the Milky Way, and there's too much to talk about here, but one highlight I would say is with Anna Bonazza, who's at Harvard right now. We've looked at stellar streams, and you know about stellar streams from your colleagues in Cambridge. You have thin streams of like maybe globular clusters or dwarf galaxies that are being disrupted in the Milky Way halo. And the streams trace out thin tracks in the halo, which are not exactly orbits, but they're very similar to orbits. And we have a good generative model. So there's something, not a good generative model, we have an okay generative model. So where we can have a disrupting object in the halo of the Milky Way and a reasonably good generative model. So we're in a situation where we can actually do information theory, and we can ask how well can we measure the properties of the Milky Way using these streams. And Anna and I looked at this question from an information theoretic point of view, and that was a very fun project. And what we found is that actually different streams give you very different information about the Milky Way. That's not surprising. And people here at Cambridge actually had written some papers that inspired us, because there were papers coming out of Cambridge saying, oh, this stream is measuring the oblateness more than this stream, which is measuring more the mass. And that had kind of inspired us. I was like, well, why don't we formalize that as a question? And so Anna ended up being able to rank every stream by its ability to measure different parameters. And there's all these parameters here. I can't even name them all, but some of them are about, the Q's are about the oblateness of the potential, and the MD is the mass of the disks. And some of them are like more sensitive to the mass of the disk, and some are more sensitive to the size of the halo or the mass of the halo. And in some cases, it's very easy to understand because of where they are and so on. But we were using it to decide, like, where should we be spending our time? What streams should we be modeling? And Anna did a really nice thing where she asked, well, what would you learn if you studied just one stream, or if you studied just two streams, or just three? Like, if we were thinking about, if you want to build a model of the streams and you just want to include the ones that you don't want to include them all because it's too hard, it gets hard fast for detailed technical reasons. Which ones would you model, in what order? And we actually have combinations, like if you want to know the velocity dispersion of the halo, you would use triangulum and GD1 in concert. That's the right answer. And it's very nice because this is like back to forecasting. It's like, what experiments should you do? We also say things in the paper about, like, when should you measure radial velocities, and should you measure radial velocities more carefully, or are they good enough? You can make decisions about using your finite resources efficiently here. And again, that has a kind of ethical component to it, as well as just being a good idea if you want to just do things efficiently. One thing that came up in that, and also comes up in the stuff I was saying about fitting out the P modes, is there's nuisance parameters, and how do you deal with Fisher information in the context of nuisance parameters? And I know that the Bayesians like to think that they're the only people who can deal with nuisance parameters. If you're a Bayesian, of course, what you do is you integrate out the nuisance parameters using your prior on the nuisance parameters. Then you get an integrated likelihood function, and then you take second derivatives of -2 log likelihood with the integrated likelihood function, the marginalized likelihood function, as you would say, where you've marginalized out the nuisance parameters. That's the Bayesian answer. The frequentist answer is that which is identical in the case that everything's Gaussian. In the frequentist answer, you basically just take the eigenvalues of a projected information tensor. And it looks like, this expression here with F prime. That's the Fisher information. The Fisher information is the subblock of the Fisher information that's not your nuisance parameters, minus the thing, which is the subblock that's your nuisance parameters wrapped in the cross blocks. It's just a standard linear algebra operation. Actually, that is exactly the operation that appears in Gaussian processes if you use Gaussian processes. Because whenever you fit a Gaussian process to something, you're marginalizing out the Gaussian process modes that are ruled out, that are like that you don't care about, and you're just trying to find what's the mean or the mean invariance of the process. Anyway, that appears in Gaussian processes as well. And there's a very nice pedagogical explanation of, like, information theory in that Albrecht paper, which is of course a cosmology paper. But anyway, there's a framework for all of that. Good. Now, what are the traditional ways we measure the galaxy? The traditional ways are not these stream fitting. The traditional ways are things like the virial theorem and the Jeans equations, and in the virial theorem you might recall is that on average, the kinetic energies of the particles is equal, in quotation marks, to the potential energies of the particles. And of course, they can't be equal because there's offsets and signs and all that stuff, whatever. But it's that they're related by a simple relation. The mean kinetic energies has a simple relationship with the mean potential energy with some 0 point. That's the virial theorem. The Jeans equations are like the next, like a much better version of that, where it's spatial derivatives of second moments of velocity are related to spatial derivatives of potentials, forces, in other words. And that, it's like standard thing you learn in, I don't know, dynamics in some, actually, physicists no longer learn Jeans equations, but astrophysicists learn them. Anyway, whatever. Actually, that might not be true at Cambridge. That would be interesting to me to know whether in the physics department, do they teach Jeans equations, or is it only to the astronomers? Anyway, in all of these cases, they're very, very beautiful. Virial theorem is amazing and very useful, actually. And the Jeans equations are very, very beautiful, but they involve measuring second moments of velocity. And that always, my alarm bells go off. Now, before my alarm bells go off, I should mention that I use the Jeans equations myself, and I love them. But I do think that they're the tool of the past. But this is here's my last paper that I will ever do using Jeans equations. That's Christina Eilers, who's at MIT, measuring the velocity curve of the Milky Way disk. And those black points have error bars on them. Check it out. And then we're comparing to the other things. The Apogee project plus Gaia is unbelievably better than everything that's happened before. It's just so much better. Now, to be fair, though the error bars we're showing there are precisions, they're like Fisher, so they're underestimates. Our true errors are larger than this, so it's not correct exactly, but the relative size of our error bars to previous work does represent how much the data have improved. The data are just far, far better, and it's thanks to Gaia and thanks to Apogee, but really Gaia. The backbone of this is Gaia. We did do a lot of distance estimation, though, using the spectra. Anyway, that was a fun project. Anyway, it's totally off topic. It's on topic is second order statistics are very hard. Whenever your project involves a second order statistic, you should be concerned. Like if you can measure H0 using just the straight up velocities and distances that you see, you're doing much better than if you measure H0 like statistically based on the power spectrum of galaxies. Just seeing the galaxies recede in distance and velocity tells you the Hubble law way better than the way the Hubble parameter appears in the physical cosmology that's predicting the second order statistics. Second order statistics are always poorly measured relative to first order statistics. It's just, it's a mess. And the worst thing about it is if you want to know the uncertainty on a second order statistic, that statistic is a fourth order statistic of your data. And I claim the thing I say here in boldface. Adrian Price-Whalen and I have been working on ways to measure the galaxy precisely using lots of stars without ever taking a second moment. Can we measure the properties of the galaxy without ever taking a second moment? And the answer is we can, but we do rely on some additional information. So I'm not going to go into a dynamics lesson, but you might remember actions and angles. If your potential is integrable, there's actions that are invariant and there's angles that wind up over time. I am aware. There's angles that wind up over time and actions that are invariant. So imagine now you take all the stars in your galaxy and you paint them with chemical abundances or some other tag that is like invariant with time. The stars that have those tags will all get wound up in the angle directions completely. They'll all get mixed in the angle directions, but they won't get mixed or not get mixed very quickly in the action directions. So the chemical abundance gradients in your galaxy have to go in the action direction. They will all get erased in the angle direction and they'll be strong in the action directions. And that means you can actually just look at the chemical abundances in the galaxy and you can just see what you might call the orbital tori. So if imagine the Milky Way is integrable. If the Milky Way is integrable, which it isn't, but imagine it's integrable. If it's integrable, then the orbits will be a foliation of tori. There'll be tori. The whole galaxy will be made of all these orbital tori that all foliate on top of each other and fill the space. And that foliation of tori is also should be the foliation of chemical abundance distributions. So each torus should have its own chemical abundance distribution, and the gradients in those distributions should go perpendicular to that foliation. So it's like this geometric look at what the galaxy should look like. But the cool thing about it is if it's true, then you see the Milky Way's orbit structure without taking any second moments. You just see it in the distribution of element abundances. And we have shown this to be true. So here, if you look at These are little phase space diagrams, VZ horizontally and Z. This is the vertical velocity in the galaxy disk, and this is the vertical height in the galaxy disk. And stars go around in loops on these diagrams. Like these are phase space diagrams, and stars do this. In fact, these are pictures of what the stars do. The middle and right panels here are what stars do. Actually, the middle panel is what stars do in that diagram. The right panel is what they do in action angle space. In action angle space, they carve perfect circles because duh. But the middle is what they do in the real space. And then you can see there's chemical abundance gradients. Each of those is one of 8 different abundances: iron, carbon, nitrogen, and so on. Those are the different abundances. And you can see the stars that are more tightly bound have different abundances than the stars that are less tightly bound. And you can just see by looking at it, you can see the orbital tori. You see they're right there. They're the contours. And that isn't quite true because these plots are projected in other coordinates, and we don't project. Adrian and I work fully in the unprojected space. So we work in the full 6 space. And in the end, I mean, it's a long story, but in the end, what we end up doing, like this is not what we do. This is like an illustrative diagram that orbits that have different, galaxies that have different disk masses in them have different shaped orbits. And so in this diagram, and so in principle, the shape of the contours in this diagram should match the orbit. That isn't quite true because these diagrams are projected, whereas the orbits, so we work in the full 6 space, not in any projected 2D space. But anyway, when we work in the full 6 space and try to understand the chemical abundance gradients in terms of an orbit foliation, we get very precise measurements of the parameters. So the little black joint contour is what we get from combining all these elements. And if you look at this diagram, I'm not going to leave this up very long, because if you look at it for long enough, you'll realize there's all sorts of inconsistencies on this diagram, which means there's some problems with the assumptions in our model, and it's all a big mess. Like all important hard data analysis problems are, it's a mess. But this allows the same kind of measurements of the galaxy that the Jeans equation does without ever taking a second moment. And we believe we can beat those second moment methods, but it does depend on some things. We will do better when there's stronger gradients, when there's more stars measured, and when they're measured better. We want more stars measured with more elements and with precise kinematics measured. So, you know, there's a lot here, but we believe that in the era of Gaia and apogee, Jeans modeling will be over. No one will ever look back at it. That's it. I've said all these things. I'm done. Thank you.
Thank you, David. That was very interesting. Let me stop the recording now.